Our first speaker this morning is Barritt Lovelace. He is Director of the UAS AI and Reality Modeling at Collins Engineers, and he's going to talk to us about advanced reality modeling and augmented reality technology applied to the Stone Arch Rehabilitation Project in Minneapolis. Okay.
Thanks, Nancy, and thanks everybody for attending, especially so early. Learning outcomes for today, I'm going to talk about our digital twin concept. I'm going to go over a little bit of a hardware and software review, talk about artificial intelligence and machine learning and how we're applying that, and then go through the case study of the Stone Arch Bridge, which kind of ties everything together that we're doing. So this concept of a digital twin, I'm sure many of you have heard it. You're probably going to hear a lot more about it. It's also referred to as reality modeling. But basically, it's any digital representation of a physical asset. So it can be a 3D point cloud or a mesh. It can be geospatially correct. We can use it to measure, annotate, and share information within that model. And I think the important thing to remember is the digital twin is a way to provide data, but probably more importantly, it's a way to communicate and collaborate around the digital twin. An example of a digital twin, this is the Tetagooch Bridge in Tetagooch State Park in Minnesota up on the North Shore. And so I'm just panning around in this model, and I'm going to zoom in. But the thing that I want you to think about is just by seeing this video now for like 5 seconds, all of you know that it's a deck truss bridge. It's painted green. You kind of can understand what environment it's in. You get a good sense of the scale or size of the bridge. And as we zoom into this gusset plate, you can see that there's been repairs made at one time. There's rivets, and there's also nuts and bolts, and you can see some corrosion. Just in that like 10 seconds, you have a really good understanding of a lot of what that bridge is. Now, if I were to put up the PDF bridge inspection report and scroll through that, it would take you a very long time to get that same understanding of what you saw in that model. So it's a way to really communicate information fast. This is another digital twin for MnDOT where we're doing inspections of the insides of box girders. And so we go in there, we mark up the walls with the cracks with marker, and then we go inside, we collect images of the inside, and we post-process those into this 3D model. And so what it saves us is first we have a really accurate model that anybody can go look at and understand what it looks like in there. But also we can bring it into CAD and do all the measurements in CAD as opposed to trying to do them in the field. And if you've ever tried to measure a crack with a tape measure in the field, everybody knows that's an approximation at best of the length of the crack. So we can get much more accurate measurements, and then the next time we do it, we can compare better and see if things are getting worse or not. I'm not going to talk a lot about the hardware that we're using, and mostly because it's not really about the drones anymore. They've developed where there's drones available for almost anything we want to do. The thing I would just emphasize is that the image quality is still really important, probably the most important factor when choosing a drone for a project. We go out, we collect all these images, and it can be thousands of images for a structure. We post-process them. For the most part, we're post-processing everything in the Bentley context capture package, which seems to create the best models and is really compatible with MicroStation, so that's helpful. But our inputs are just our images with the geotags. It could even be video frames. We usually have ground control points, and sometimes we're using QR codes, which the software can recognize and help tie everything together. If you're just getting into using drones, I think one of the easiest and best applications for it is doing deck surveys. This is a bridge we did in North Dakota where we flew the bridge, and we're able to bring it into CAD and delineate all the cracks in CAD and quantify them that way. So we have a nice record of what's there, and we get really accurate quantities, and it's much faster than trying to measure all those cracks, especially if you consider that we don't have to close the bridge to do this. If we take it one step farther, we can start using artificial intelligence to find those cracks automatically. And so we do the same thing. We fly the bridge. We put it into our software programs. We've been using, there's a software from Fujifilm and also from Bentley to do the automatic crack detection. Usually the way it works is it will sometimes maybe overestimate where there's cracks, but it's really easy to just go in and delete the ones that we know aren't cracks. And in the end, it's far more accurate than somebody trying to measure them in the field. And again, then we can compare them on future cycles. This is just another example of using AI for a masonry bridge. This is the context capture software, so we're finding the cracks in the masonry. Another example of using AI, and everybody hears AI all the time, but we don't realize maybe that we're already using it in a lot of ways, and crack detection is the most obvious one, but the other way is that we are using AI for data collection. And in this case, we're using the Skydio 2 drone, which has a 3D scan app. And basically all we do is we tell the drone a volume that we want to map, and the drone goes out and explores that volume and looks basically to see what's in that volume, and then creates its own flight plans to capture all the images. And so we push start, and it flies completely by itself, takes all the images that you need to create a 3D model. And it's significant because it puts it in so many more people's hands to be able to do it, because collecting images for a bridge model can be kind of an art and can take trial and error to get it right. But being able to use an application like this where you just know you're going to be successful right away is really pretty neat. Our Stone Arch Bridge case study, the bridge is located in downtown Minneapolis. It's a 22-span masonry arch bridge, was opened in 1883. It's 2,100 feet long and was built by James J. Hill for his Great Northern Railroad. It was a railroad bridge, I think, up until about the 70s, and then was abandoned for a while and was reopened as a pedestrian bridge in the 1980s. And it's probably the most historically significant bridge in Minnesota. And we are currently just finishing a rehab of this bridge. We're doing final plans right now. So the workflow when we're incorporating UAS and digital twins is the very first thing we do is we go out in the field, we capture all the data, we create a digital twin of the bridge, and then we take that digital twin and we upload it to ProjectWise. And we gave all of our inspectors tablet computers, and so they were able to take those models out in the field with them on the tablet and put all of their inspection notes right on the model in the field. And that turned out to be a huge time saver and also a much, much more accurate way to record the notes, because instead of having to describe where something is or sketch it or draw it on a plan sheet that maybe the scale doesn't work right, you're able to put that note right in the exact spot that it is in the world and not worry about describing it. And then we're going through the rehab and design plans now, and then we will also give those models to the contractor for their planning purposes and even to help bid the project. So when we do the inspection planning for the flights, almost all the flights are completely automated. We just plan them in a 3D environment before we go out there. Now this is a video, it might not work, but basically the drone just flies these lawnmower patterns on the bridge and creates images so that we can post-process them into the model. And for this bridge, we collected almost 9,000 42 megapixel images. We had 35 ground control points. It took us 4 days in the field, and we had 2 to 3 team members doing the work. The third team member is when we're operating closer to the public. Their job is just to answer questions because it's a very busy area, and so you get a lot of I call them retired guy questions, so which I'm sure I'll be one day as well, but so we have that third person to kind of keep the pilot able to focus. And for the most part, we use the Intel Falcon 8 drone, and then also the Skydio drone in some areas that were really tight. So this is what the reality model or digital twin looks like. This is just 6 spans of the 22 spans of the bridge, but gives you an idea of what the deliverable is. These are all the inspection notes that were populated during the inspection for these spans. So you can see there's a lot of notes that we take because we're, doing individual notes for stones and mortar loss and those kinds of things. So you can imagine how much time it would take to try to sketch all that stuff. And so this was much faster, and then we're able to pull it right into CAD as well. And all these models that we create are tiled so that if we're zoomed out far, you're not pulling as much data, but as you zoom in, you're pulling more data and more detail. So this, it almost looks like a picture, but it's really just the 3D model. It almost approximates being right in the field. One of the unique things about this project is that the Army Corps of Engineers drew down the pool. It's right between 2 lock and dams, and they drew it down for their own purposes, but we took advantage of that, and we went out and reflew these portions of the bridge that were normally underwater, and we normally collect information using just doing diving. But this was a unique opportunity to collect all that information and have it for design while the water was drawn down, so we could see all the riprap and everything. And so this is the model of the bridge during the drawdown. And if we zoom in, this is the kind of the level of detail that we can see. So we can see that there's riprap and then on the downstream side of these piers, there's aggradation of sand. We can see the exposed reinforcement. So we're planning all of our repairs based on these models. And like I said, we can pull it directly into CAD, and we still have to create a digital or a traditional plan set. And I think soon we're going to be moving away from that as owners get more comfortable doing 3D delivery. But for now, we can still take advantage of those digital twins and pull them into the CAD drawings, which gives a lot of context about the bridge. One of the things we've been working on lately with Bentley is doing these mixed reality inspections, and we're doing it with the Microsoft HoloLens. And Bob's going to come up here in just a second, and we'll show how this works. But so we have these digital twins that we can view through this augmented or mixed reality environment, and it's really beneficial because we can kind of approximate being in the field. If we're looking at these models through our computer screen, we can do a lot with them, but you don't get that sense of scale. So by being able to view it through the mixed reality, then we can sort of do these virtual inspections of the bridge, which is pretty neat. So I'll have Bob come up and we'll plug it in and I'll show you what it looks like. This is just a video of what it looks like using it in my office. So this is what Bob is seeing through the HoloLens, and he's just using those menus with hand gestures. And so you can see, it's basically just like being in the field, and we can annotate those models within that just using hand gestures. We can make notes, and then all of that information gets populated back into the models that are on the cloud or on the computer, so somebody else could view them on their computer. And all of this is shared, so all these models are shared with everybody on the project team, and everybody has access to them. And if you have a HoloLens, then you can view it through the HoloLens. And I think the neat thing too is that not everybody has the opportunity to go out into the field to see the bridge in person. And that may be because they're not physically able, or they're too far away and the budget doesn't allow it. So it's a great way to get the designers involved and be able to sort of visit the bridge in the field. And the one thing that I think we've really found is that, usually you do a really detailed inspection for a project like this, but then that's all the data you have for the rest of the project. But in a way, every time we have a question, we can sort of revisit the bridge in the field to check things. And even, we're finishing our design right now, and the designers that are working on it right now are sending me messages and texts, and they're clipping parts of the reality model and saying, hey, in this area it sticks out farther than we thought, we have to change our detail. And those discussions would be really difficult without having the model, because we'd have to describe it. Not only does the model have a better way to communicate, but we're reducing risks on our project as well. So thanks, Bob. And if you want to see it in person, you can stop by our booth if we're still open, or the Bentley booth as well. The benefits of doing these new methods is the improved data quality. It reduces risk for the designers because we can make good decisions about stuff. And I think most importantly is we're not making conservative decisions so we're reducing risk for the designers, and we're not making these really conservative decisions because we're not sure what's out there. And we also feel like we're going to reduce risk for the contractors. Much better collaboration with our team. We often have meetings that are sort of centered around these models, and we can talk about it. The safety improvements are important. We don't have to close the bridge as much for snoopers and that sort of thing. And one of the biggest things is that our traditional bridge inspection report for the Stone Arch Bridge is about 6 megabytes, and we've collected 2 terabytes of data. So we have an over 300,000 times increase in data that is available to us. So that's pretty important. So I guess the last thing is I just want to talk about some of the implications for our industry. I think we have like a pretty big shift in our project workflows that is coming. Data is so important in so many other industries. We've seen the Googles and Facebooks and become these massive industries just based on data. And so that same transformation is happening in our industry, and we have to be prepared for it. So the kind of staff that we need is going to change, or is changing, and we need to embrace robotics and AI and machine learning as we move forward, especially with our workforce, maybe not keeping up with the demand. We have to find more efficient ways to do it. And really, to make these things work, we have to be willing to abandon some of our traditional methods, such as doing, regular plan sheets. The challenge is in the interim, we kind of have to do both. And to really take advantage of it, we need to kind of make that leap to the next way of doing it. That's all I have. I'll take any questions.
An easy one is with the crack detection, and you might have mentioned it and I missed it, but what technology or software are you using to define the cracks in the bridge deck? Is that something?
There's 2 ones we're using right now. The first one is, I think it's by Fujifilm. It's infrastructure. I can't remember the name. That's one that we're using. And then Bentley is also developing one. There's one that is part of context capture right now. And we're working with actually people in France and different places in the world that are refining some of the algorithms and trying to base it on our specific bridge needs. So based on different condition codes, so that we can automatically classify the cracks based on their widths.
First off, beautiful model, very cool stuff.
Thank you.
I was wondering what kind of image overlap you were using to get that level of quality.
Good question. So when we take our images to create our model, we need to have a large amount of overlap. And the reason we do it is we want the same points in a whole bunch of different pictures, and that's how the computer triangulates and uses trigonometry to create the 3D model. And for like a normal drone mapping mission, you might do like 80% or something like that. But when we're doing bridges, they're probably the most difficult thing there is to model, because you have the top and the underside of the bridge and then the ground. And so we're probably closer to like 95% overlap and doing more overlap in some of the more challenging areas. So a bridge is an asset that you have to do probably way more overlap than you normally would.
9,000 images, thank you. You had 9,000 images, but you used only 35 ground control points. In our experience, those ground control points improve accuracy quite a bit. Did you ever check the accuracy of drone imagery with some sort of survey?
We will often put out, we have like I'm not sure what you call it, but it's just like a tape almost that's 6 feet long, and it's kind of a survey target. And so we'll put that out and use that to check. And then we'll also just check known points. Actually, for us, the bridge is only 2,000 feet long, so 35 ground control points is quite a few for that. But even when we don't use ground control points at all, we can often get within a centimeter for distance. The ground control points help us more with being geospatially correct. But even without them, we can get enough accuracy for doing most of the things we need to do. We like to use them anyway because it just gives us some assurances that it's accurate. But it is really important to check.
So when you're doing the deck mapping, what elevation are you flying at, and what kind of accuracy are you seeing on crack widths to be able to determine condition state on those cracks?
So that's a good question. And the height depends on the sensor we're using. So if we're flying the Intel, which has either 36 or 42 megapixel sensor, we try to fly it at like 40, 50 feet to get really good resolution. When we're using the Skydio 2, we have to fly even lower because that has a smaller image sensor. And I would just say the biggest lesson learned in doing all of the modeling, whether it's for crack control or just being able to see details, is you have to fly really close to the bridge to get good detail. And that's one of the things that is, I think, the biggest lesson for people to learn. They'll fly it at like 100 feet away, and you just don't get enough detail to be able to do inspection type stuff. It depends. Most of the time we don't. So if we're flying the Intel at 40 feet, we can fly, and we're well over traffic. We can stagger it so that we're not directly over traffic. We can take pictures at an angle so we don't interfere with traffic either. But the Skydio gets a little more challenging.
The preceding was produced by the National Center for Pavement Preservation. More information can be found on the web at pavementpreservation.org. Additional support provided by Michigan State University.